More programming. So I'm working through SICP, Structure and Interpretation of Computer Programs. And I've got Dr. Racket open and Scheme loaded up so that I can do stuff interactively. Okay, so let's start reading again. To evaluate a combination whose operator names a compound procedure, the interpreter follows much the same process for combinations whose operators name primitive procedures. So this is a bit of a mouthful of a sentence, but basically I think what it's saying is that the interpreter follows a similar process for doing a compound procedure. A compound procedure is just like something that's built out of primitive procedures. So like primitive procedure is like, addition, multiplication, whatever. And then compound is built on top of that and uses that. And basically the interpreter follows like a similar process for evaluating those procedures. So you see, that is, the interpreter evaluates the elements of the combination and applies the procedure, which is the value of the operator of the combination, to the arguments, which are the values of the operands of the combination. All right. So we can assume that the mechanism for applying primitive procedures to the arguments is built into the interpreter. For compound procedures, the application is as follows. To apply a compound procedure to arguments, evaluate the body of the procedure with each formal parameter replaced by its corresponding argument. We're going to illustrate. So this combination, this procedure that they're referencing, F, is built on. Oh, that's handy. That it shows you the link. That's very learning oriented. I like that. Right. So this is from here. This is from 1.14. The F procedure is defined in terms of sum of squares, and it basically. So here's how it works. You put some number into F. You feed some number into F, and then this F procedure takes that number, and to one instance of that number it adds 1, and to one instance of that number it multiplies by 2, and then it takes the result of those and finds the sum of squares. And a sum of squares procedure uses square, and the square procedure uses multiplication, and multiplication is a primitive, which goes back to the like basic definition of this programming language. And so there we are. So that's the sort of structure of this operation. So they're basically going through this. They're saying, okay, so first step is you get this, and then you replace the formal parameter, which is a, with the actual thing. And again, oh, that's cool how it shows you the links. So basically when you feed a into here, you get a 5 here and a 5 here, which they illustrate, right? So thus the problem reduces to the evaluation of a combination with two operands and an operator sum of squares. I mean, like, this is one, we have to go, there's more steps in the analysis, but at this level, we have one operator, which is this thing, and then the operands, which are this is one operand, and this is one operand. An operand is just like the thing that the operation is being done on. So it's like this is the operator, and this is an object of the operation, and this is another object. It's just a fancy word for that. So they say, thus the problem reduces to the evaluation of a combination with two operands and an operator sum squares. I already read that. Evaluating this combination involves three subproblems. We must evaluate the operator to get the procedure to be applied, and we must evaluate the operands to get the arguments. So this is just saying, like, we've got to figure out what this requires and then what these values are. So these values are pretty straightforward. 5 plus 1 is 6. 5 times 2 is 10. So that's straightforward. And that's what they say. So then that's what you're applying sum of squares on. And sum of squares is just the sum. I mean, it kind of tells you. It's like the sum of the squares of one number and another number. So when we do this step, we've got 6 and 10. So sum of squares of 6 and 10, right? So then this is the content of sum of squares. So sum of square of 6, which is 36. The square of 6 is 36. And the square of 10 is going to be 100. So that's what they're talking about here. And then they do the operation. And they finally do the addition, and they get f of 5 is 136. And because we defined all this stuff like we built up, we started with multiplication and we used f for square, and then we did sum of squares, and we did this function thing. And so we built up this tower of abstractions, and then we could just have the computer do all that calculation. So the process we have just described is called the substitution model for procedure application. It can be taken as a model that determines the meaning of the procedure application insofar as the procedures in this chapter are concerned. However, there are 2 points that should be stressed. What are the 2 points? So, the purpose of the substitution is to help us think about procedure application, not to provide a description of how the interpreter really works. Typical interpreters do not evaluate procedure applications by manipulating the text of a procedure to substitute values for the formal parameters. In practice, the substitution is accomplished by using a local environment for the formal parameters. We will discuss this more fully in Chapter 3 and 4 when we examine the implementation of an interpreter in detail. Over the course of this book, we will present a sequence of increasingly elaborate models of how interpreters work, culminating with a complete implementation of an interpreter and compiler in Chapter 5. The substitution model is only the first of these models, a way to get started thinking formally about the evaluation process. In general, when modeling phenomena in science and engineering, we begin with simplified, incomplete models. As we examine things in greater detail, these simple models become inadequate and must be replaced with more refined models. The substitution model is no exception. In particular, when we address in Chapter 3 the use of the procedures with mutable data, we'll see that the substitution model breaks down and must be replaced with a more complicated model of procedure application. They're just saying, this is a simplified presentation. This is like the first layer of the onion, or the first circle in the spiral of the learning journey of SICP in terms of how procedures work, and that's fine. you can't take in everything at once. So what's the footnote? Despite the simplicity of the substitution idea, it turns out to be surprisingly complicated to give a rigorous mathematical definition of the substitution process. The problem arises from the possibility of confusion between the names used for the formal parameters of a procedure and the possibly identical names used in the expressions to which the procedure may be applied. So, according to the description of evaluation given in 1.13, the interpreter evaluates the operator and operands, meaning fully evaluates them, and then applies the resulting procedure to the resulting arguments. This is not the only way to perform evaluation. An alternative evaluation model would not evaluate the operands until their values were needed. Instead, it would first substitute operand expressions for parameters until it obtained an expression involving only primitive operators. So basically, in the previous example, the interpreter evaluated 5 plus 1 and 5 times 2 right away, and then figured out the sum of squares of those. Whereas with this alternate order, basically nothing gets, it keeps substituting the lower levels of until it gets to a version where basically everything is primitive, everything is either addition or multiplication or subtraction or division or whatever it is, and then it evaluates. So whereas before it did sum of squares on 6 and 10, here it's like, okay, sum of squares means square of this and square of that, and it doesn't touch the 5 plus 1 and 5 times 2. And then square means multiplying a number by itself, and it's only here that it starts to evaluate these. And so you notice, so they say, this gives us the same answer as our previous evaluation model, but the process is different. In particular, evaluations of 5 plus 1 and 5 times 2 are each performed twice here, corresponding to the reduction of the expression x times x, with x replaced respectively by 5 plus 1 and 5 times 2. So yeah, because the way it's treating these, right, so I think by an alternative evaluation model would not evaluate the operands until their values were needed. It basically just means like you basically do as much substitution for the procedures as you can, and then you literally can't do anything else until you start doing the evaluation. So I think that's what until their values were needed means. This alternative fully expand and then reduce evaluation method is known as normal evaluation order, in contrast to the evaluate the arguments and then apply method that the interpreter actually uses, which is called applicative. It can be shown that for procedure applications that can be modeled using substitution, including all procedures in the first 2 chapters of this book, and that yield legitimate values, normal order and applicative order evaluation produce the same value. Okay. List uses applicative order evaluation partially because of the additional efficiency obtained from avoiding multiple evaluations of expressions such as those illustrated with 5 plus 1 and 5 times 2 above. And more significantly, because normal order evaluation becomes much more complicated to deal with when we leave the realm of procedures that can be modeled by substitution. Normal order evaluation could be extremely valuable. Okay. Conditional expressions and predicates. The expressive power of the class of procedures that we can define at this point is very limited because we have no way to make tests and perform different operations depending on the result of the test. For instance, we cannot define a procedure that computes the absolute value of a number by testing whether the number is positive, negative, or zero and taking different actions in different cases according to the rule this. This construct is called a case analysis. And there is a special form in Lisp for notating such a case analysis. It's called cond, which stands for conditional, and is used as follows. Right, so I played with this expression, this expression, sum, and you can see, because basically, if you give it a number greater than x, it just outputs x. If you give it a number equal to 0, it just gives you 0. And if you give it a number less than 0, then it negates it, so then it becomes positive. So you've got an absolute procedure for getting the absolute value. Actually, though, let's try something. Oh, yeah. Yeah, it works on. Okay. Just want to make sure. Actually. Limit. Oh, yeah. It truncates it. Okay. Good to know. All right. So the general form of the conditional expression is P1, E1, yada yada, consisting of the symbol cond followed by parenthesized pairs of expressions called clauses. The first expression in each pair is called a predicate. That is, an expression whose value is interpreted as true or false. Conditional expressions are evaluated as follows. The predicate P1 is evaluated first. If its value is false, then P2 is evaluated. Predicate's kind of a weird name for a thing that's getting evaluated first, but so it continues. So basically goes through each predicate, and these are the predicates. This one, and this last one. And it goes through and tries to find the value, and then if none of the p's is found to be true, then the value of the cond is undefined. Yeah. Expected a real, I gave it a banana. That's what happens. The word predicate is used for procedures that return true or false, as well as for expressions that evaluate to true or false. The absolute value procedure, ABS, makes use of the primitive predicates greater than, less than, and equal to. These take two numbers as arguments and test whether the first number is respectively greater than, less than, or equal to the second number, returning true or false accordingly. Another way to write the absolute value procedure is define abs x cond less than x0. I see. If x is less than 0, return the negation of x, otherwise return x, which covers the 0 case because then you just return 0. Right. Else is a special symbol that can be used in place of the predicate in the final clause of a cond. This causes the cond to return as its value the value of the corresponding. I skipped over this because I was like, wait, what's E? Is it expression? So it loops through. Cond goes through each of these. Not loops, but just goes through. And this process continues until a predicate is found whose value is true, in which case the interpreter returns the value of the corresponding consequent expression E of the clause as the value of the conditional expression. Okay. Back to here. If you use else, it causes the cond to return as its value the value of the corresponding consequent expression whenever all previous clauses have been bypassed. In fact, any expression that always evaluates to true could be used as the predicate here. And yeah, okay. Here's yet another way to write the absolute value procedure. Or actually, let's try this. Oh, I see. So because we're using this less than, then it's expecting a number. And so if you try and feed it like a string or whatever, a word, then it beeps at you. I wanted to see if it would still beep with this rewrite. Here's yet another way to write the absolute value procedure. So if x is less than 0, negate otherwise x. Right, so here we're using if. This uses, let me paste this in here. This uses a special form if, a restricted type of conditional that can be used when there are precisely two cases in the case analysis. The general form of an if expression is if predicate, consequent, alternative, right? So if this, then this, otherwise this, basically. To evaluate an if expression, the interpreter starts by evaluating the predicate part of the expression. If the predicate evaluates to a true value, oh, now I'm thinking about it, because I guess you have the operator and then the predicate, right? So maybe predicate makes sense as a word. So to evaluate an if expression, the interpreter starts by evaluating the predicate part of the expression. If the predicate evaluates to a true value, the interpreter then evaluates the consequent and returns its value. Otherwise, it evaluates the alternative and returns its value. What's the footnote here? A minor difference between if and cond is that the consequent expression part of each cond clause may be a sequence of expressions. If the corresponding predicate is found to be true, the expressions E are evaluated in sequence, and the value of the final expression in the sequence is returned as the value of the cond. In an if expression, however, the consequent and alternative must be single expressions. Okay. In addition to primitive procedures such as less than, equal, and greater than, there are logical composition operations which enable us to use to construct compound predicates. most frequently used are, looks like and, or, and not. It gives a description of and. The interpreter evaluates the expressions E one at a time in a left to right order. If any E evaluates to false, the value of the AND expression is false, and the rest of the E's are not evaluated. If all E's evaluate to true values, the value of the expression of the AND expression is the value of the last one. So regarding AND, I made this little expression here, and I was playing with it some, and yeah, it's basically, it's what you would expect if all the expressions evaluate as true, then you get true, and if any evaluate as false, then you get false for the AND. So that's pretty straightforward. Like obviously 5 is false because this is greater than 5. So, okay. For OR, the interpreter evaluates the expressions one at a time in left to right order. Any expression evaluates to a true value, that value is returned as the value of the OR expression, and the rest of the expressions are not evaluated. Right. So you do the same thing. So here we get true for this, because, well, 2 is not greater than 5, it is less than 10. So that's pretty straightforward. The value of a not expression is true when the expression E evaluates to false. Right. Notice that and or not are special forms, not procedures, because the expressions are not necessarily all evaluated. Not is an ordinary procedure. Right. Because and or take more than one expression, so you might not. So for and, it stops when it hits the first false expression, or it stops when it hits the first true expression. For not, I guess there's only one expression. All right, so I need to find a predicate test for whether one number is greater than one number is greater than or equal to another. You need to see, this is the name. That could be a little confusing, but this is the name of the function. It's not an actual operator. Like, in the same way that absolute was the name of a function. And this function is gonna evaluate to true if either x is greater than y or x is equal to y. And so I just tested it out. And when I put 5 and 9, it said false because 5 is not greater than 9. But when I flip them, it said true. So I guess I'll... There we go. Yeah, it's all good. Find the same function basically, or I guess the same, yeah. Alternatively as, right. Because this, whenever this is not true, then whenever x is not less than y, it's got to be either equal to or greater than y logically. So I'm not even gonna, I think I get the idea there. Okay, exercises, yay. Below is a sequence of expressions. What is the result printed by the interpreter in response to each expression? Assume that the sequence is to be evaluated in the order in which it is presented. So I guess they're just checking that you know how the operations work. So I'm just gonna start here because this is the first like interesting one. So I mean, it's not really interesting, but like these are all like kind of silly. So we're doing, what is it? Applicative order. This is 8. This is -2. And we add 8 and -2 and we get 6. Yay. Okay. So I guess these like build on each other. Like you're supposed to enter each. And because like here we have B being defined in terms of A. And when you first define something, I guess the interpreter is not going to spit anything out until you type the name of the thing that you defined. But anyway, so I guess we'll do that, and then nothing get spit out. And then, so B is basically, because A is 3, so 3 plus 1 is 4. So A is 3 and B is 4. So this is going to be 3 plus 4 plus the result of this, which is 12. 4 plus 12 is 19. There we go. This is going to be false. There we go. Oh, I guess maybe assume the sequence is to be evaluated in the order in which it is presented is basically telling us that some of these are dependent on the earlier ones. Ooh. Okay. So the meaning of this is basically if, because remember, A is 3 and B is 4. So if it's both the case that 4 is greater than 3, that's true, and 4 is less than 3 times 4, and 3 times 4 is 12. So if 4 is less than 12, which is also true, then output 4, otherwise output 3. If you run that, it outputs 4, which you would expect because this is all true and it's going through an AND. So if it's all true, then it'll do the first thing. Cond. So this says if 3 equals 4, output 6. If 4 equals 4, so okay, 3 does not equal 4, so you skip that. If 4 equals 4, and that is true, then do the sum of 6, 7, and 3, which is 16. Otherwise, output 25. So I would expect 16 from this. Yep. This is an interesting one. So basically, if 4 is greater than 3, then output 4, otherwise output 3. But then the output is added to 2. So because 4 is greater than 3, I would expect you to have a 4 here, and then that would get added to 2, and you would have 6. All right. So if 3 is greater than 4, yeah, put A. That's not the case. If 3 is less than 4, yeah, put B. Else -1. So we would only hit the else if 3 was equal to 4. If A was equal to B, I should say. Which it can't be because 3 is not equal to 4. So now since based on the actual values we have for A and B, we're going to do this one. So we're going to get the value B out of this whole cond. So that's 4. And that 4 is going to be multiplied by the sum of A and 1. And A is 3. So the sum of 3 and 1 is 4. So you get 4 times 4. So I'd also expect 16 from this. There we go. Cool. One exercise completed. Now I'm a full programmer. Okay. I can't even read this. Like, what the hell is this? What is going on here? Like there's, you can't even make out the denominators, man. What's going on? I mean, I guess this was like it was taken from some ancient text. I'm just gonna skip this one for now. Define a procedure that takes 3 numbers as arguments and returns the sum of squares of the 2 larger numbers. Alright, so tried 1.3, and so what I'm trying to do here is like, okay. So roughly the structure is if x is the lowest number, then do sum of squares of y and z. If y is the lowest number, do sum of squares of x and z. And if z is a low number, do sum of squares of x and y. And to find the lowest number, I basically did if x is less than or equal to y and x is less than or equal to z. So what that means is that x will at most, so for this first line here, that's checking for x being the lowest number. If x is at most equal to y or z, or both, then it's fine to use y and z for the biggest numbers. Because at most, like you'd have a scenario where like x and y are the same and z is bigger. Like this one. And so the program will use y and z, and that's totally fine, for figuring out the sum of squares, and that's fine. Even though y isn't actually bigger than x, they're the same, so it doesn't matter. Doing less than or equals to on all these catches the case where you feed it numbers that are all the same. Just did less than, you wouldn't capture the, like if you feed it 5, 5, 5, it doesn't know what to do. If these were just less than, like I tried it earlier. But with this way of setting it up, if you feed it 5, 5, 5, it says, okay, well, x is less than or equal to y, and x is less than or equal to z, because they're all equal. So then it says, okay, well, I'm going to do y and z. So I think that's right. So regarding 1.4, I'm not sure I quite follow their point in asking the question, but I do think I can describe the procedure. So I'll say that. So basically, the purpose is to add the absolute value of b to a, And so you feed the procedure an A and a B, and if B is greater than 0, it just adds the B to A normally, and if B, and otherwise, it adds the negation of B to A. So that's pretty straightforward, and it works like you would expect. So Ben Bediddle has invented a test to determine whether the interpreter he is faced with is using applicative order, evaluation, or normal order. So I think this must be actually jumping back to 1.4. Like this must be the point of this is like it's a model of evaluation allows for combinations whose operators are compound procedures because we're doing applicative order, I guess. Now let's look at 1.5. Ben Bediddle has invented a test, yada yada. He defines the two following procedures. Define P, define test XY. If X equals 0, 0. Otherwise, Y. Since I think I'm still a bit fuzzy on applicative versus normal order stuff, I'm going to stop here, and I might like watch some lecture or something about applicative versus normal order, or find some other discussion and see if that helps, and come back later.